Section 2.4, we're going to be looking at more differentiation rules. And so we have power rule, product rule, quotient rule, and now we picked up this chain rule. So for this section, I want to look at some examples of functions that we have not worked with yet. So the first one I want to look at is, what do we do if we have the absolute value of a function? And so let's look at this one here. The derivative with respect to x of the absolute value of u is going to be equal to, what you're going to do is you're going to draw a fraction bar. You're going to put what you're absolute valuing on bottom, do not change it. You're going to put what is inside the absolute value bars on top, do not change it, times the derivative of u. So let's kind of see what that looks like with some numbers. And so if I want to take the derivative with respect to x of y equal to the absolute value of 4x, then what we're going to do is we're going to say y prime is equal to, I'm going to draw a fraction bar. I'm going to put my absolute value of 4x on bottom. Don't change it. Whatever you're taking the absolute value of, you're going to put on top. Don't change it. Times the derivative of 4x, which is 4. Clean it up. So I'm going to multiply 4x times 4. That gives me a 16x over the absolute value of 4x. So it's not as bad as some of those we ended the last lecture with, but you do have to know the form of it. And so knowing, again, this piece right here. And so you're going to see some of those examples on the homework. And again, still use any rules that you have previously in lectures. Now what we want to do is we want to look at natural logs. We haven't looked at any exponentials or logarithmic equations, and so let's pick up the idea of what is the derivative of a log. The derivative of a log is going to be equal to, again, it's going to be a matter of formatting it like we did with the absolute value. So you're going to draw your absolute value, you're going to draw your fraction bar. Whatever you are logging, you're going to put on bottom. Don't touch it. Times the derivative, or on top, the derivative of what you were logging. And so whenever you're taking the derivative of a natural log, we'll deal with log of other bases later, you're going to do u prime over u. Whatever you're logging on bottom, and its derivative on top. Let's move into these three examples here so you can kind of see the logistics of what's going on. So I'm going to say y prime is equal to, whatever I'm taking the natural log, I'm going to put it on bottom. The derivative of whatever I have on bottom, 10x squared, would be 20x, and I place it on top. That's my raw derivative, so I'm going to clean it up. 20 over 10 reduces to 2. X over x squared reduces to just x. Let's do it again. ln of 5x, so its derivative would be, put whatever you're taking the natural log of on bottom, put its derivative on top, and then clean it up. So that gives me 1 over x. Let's do it again. Y prime would be equal to, whatever you're taking the natural log of on bottom, whatever its derivative is on top, and that would be your answer. So you can tell that from these two examples, if it's just an x and there are no exponents, then it turns out to always be equal to this 1 over x, because you're getting that constant, or that 5x, to cancel. So if we have a conversation about the natural log of x, that's naturally going to lead into our exponential. Let me go ahead and highlight this rule here. And so let's look at the exponential of e to the u. Now we're saying e to the u in the fact of, a lot of times you're going to see that u meaning that any given function that's up there. So what's the derivative of this one? When you go to do e to the u, you just write your exact problem again, times the derivative of your exponent. You're going to write your problem again, e to the u, times the derivative of your exponent. And that's going to be your rule for working with an e. So let's do that. So this would be y prime is equal to, rewrite your e to the 6x, times the derivative of your exponent, which is just 6. Going back to when we were doing formatting with our trig functions, it's better if we just go ahead and put that 6 on the front end so we don't mess it up in any way. And then we're done. Let's do this next one, a little bit more complicated. That's y equals e to the 5x cubed. So this would be y prime is equal to, rewrite your exponential, times the derivative of your exponent, which is 15x squared, and then rewrite it in a better form. Not too bad. So now we've picked up our absolute values. We have picked up our exponentials. We've picked up our natural logs. Now, natural logs and exponentials are both base e. That's what they're dealing with. So let's look at what happens when we're dealing with other bases other than e's. So we're going to look at this here. The derivative with respect to x of log base a of u. That's going to be equal to, draw your fraction bar, whatever you're logging on bottom, its derivative on top. And then here's the one difference, because we're not in base e, we have to say ln of a. And you can see we don't have ln of e when we do our other problems, because ln e, if you remember back to your algebra days, ln e is just 1, and so it ends up canceling out. So this is going to be our form for doing logs of any other base other than e, and it's just adding that ln a on the bottom. So let's look at that example. So if I'm going to do y prime of this, I'm going to draw my fraction bar. I'm going to write whatever I'm taking the log of on bottom. I'm going to write its derivative on top. And I'm going to do ln of the base in the denominator. As always, clean up as much as you can. So this would be equal to 1 over x ln 8. And again, I like to put my x in the front so I don't accidentally multiply that 8 times x, and I keep that ln kind of separate. So there's our log base a. Let's do exponentials that are base a. So when we're writing this, it's going to be very similar to what you did with your e. So you're going to say, rewrite your exponential times the derivative of the exponent. See, real similar to e. Just like what we did when we switched to log base a, now I have to have ln a in the front. And you're going to see me do these 3 parts every single time. I'm going to write my original problem. I'm going to write the derivative of the exponent. And then in the front, you're going to see me write ln of the base. So this is your form or method for doing a to the u. And so let's work out this one. So this one will be y prime. So I'm going to do 3 parts. I'm going to rewrite my exponential. I'm going to say times the derivative of the exponent. And then I'm going to do ln of the base out front. And just be careful when you go to type this in. I would keep your parentheses around these 2 outer pieces. So again, you don't overwork or combine something along the way. And so look at that. We've picked up 2 more methods or 2 more forms of working with it. So now that we have our 5 different methods, absolute value, log, natural log, e's, base a, let's move into some more examples. Let's first work with these natural logs. Now I want to move into these examples because I want you to see how we can integrate the rules we already know with these rules that we've picked up. And so this would be equal to, the derivative would be, so I could say what would be this derivative? I'm going to draw my fraction bar. Whatever I'm natural logging, I'm going to put on bottom. I'm going to take the derivative of what I just wrote and put it on top. And then I'm going to clean up if need be, but you can see this one, there's really no cleanup to be had. Then I'm going to go to the next one. Okay, this one has x times ln x, and so this is a product of 2 functions. So we are going to have to do product rule, but then also remember our rules for natural logs. So first I'm going to do the derivative of the front, which is just 1, times the second, plus the front, times the derivative of the second, which ln x, we saw that in previous examples, is just 1 over x, or again, natural log of whatever you're taking the natural log of goes on bottom, which is x. Its derivative is just 1 on top. So that's my raw derivative. I absolutely need to clean this up. This gives me ln x plus, these are going to cancel each other to give me a big old 1, and that would be my final answer. Next one. This one we're going to have to implement chain rule. So I'm going to say, okay, its derivative would be equal to this 3. I'm going to have to bring out front. So I'm going to say 3 ln x, subtract 1 from the exponent to give me 2, times the derivative of ln x. So I'm going to put when I'm natural logging on bottom, its derivative on top. And then as always, clean it up. So that would give me 3 ln x squared all over x. Let's do another one. F of x is equal to ln square root of x plus 1. So as always, when you have a radical, first do some algebra. So this would be x plus 1 to the 1/2. Next, we're going to have to pull up some algebra of logarithms. We're still not getting into calculus. If you remember from rules of logs, that if you have something being raised to a power, that you can pull that power out front, and it would just be n ln of a. And that was a property of logarithms. Again, I'm in red. This is just algebra. So the next step I'm going to do is I'm going to rewrite that as a 1/2 out front ln of x plus 1. And if you need some kind of recap or resources to remember those rules of logs, just shoot me a message. I'll be happy to help. So now here's my function. I am looking at what is the derivative of 1/2 ln of x plus 1. Well, when I go to do derivative, I know that coefficients just to go along for the ride. So 1/2 is just going to stay out front. Then I'm going to do my derivative of the natural log of x plus 1. So remember, you put what you're natural logging on bottom, and you put its derivative on top. So then just the cleanup of this, I multiply across the tops and bottoms, multiplying fractions. That gives me 2 times x plus 1. And that would be my derivative. So the good thing about natural logs is that when you're working them, you can apply your algebra concepts, and really that's going to make your life a lot better so that you're not having to divulge into product or quotient rules possibly. And so what I want to do is let's do a little bit harder natural log, and let me show you how those properties can help us. And so here's my problem. If I were to approach this with doing no algebra, then I would have to do not only the rules of natural logs, but I would also have to do the rules of product in my numerator, quotient, because I have a fraction here, and that just scares me. And so I'm going to have another review here over to the side. Remember rules of natural logs. We've already picked up that if we have a to the n, that we can pull that n out front, and it is equivalent to n ln a. Other properties you have is that if you were taking ln of AB, that you could expand that, and that's ln A plus ln B. If you have ln of A over B, then that turns into subtraction, A minus B. So we are going to put these algebra rules of working with logarithms into play here to apply our algebra before we do our calculus, because it's really going to make your life a lot easier. So this is going to be f of x is equal to, well, first I'm going to separate out this division. And so that gives me ln of x times x squared plus 1 squared minus ln of the square root of 2x cubed minus 1. So next I'm going to go ahead and get rid of that radical and change it to a fractional exponent. And so then that gives me 2x cubed minus 1 to the 1/2. Next I'm going to expand out this multiplication. So that gives me f of x equal to ln x plus ln of x squared plus 1 squared minus ln of 2x cubed minus 1 to the 1/2. Lastly, I'm going to apply what we did in the last problem, and I'm going to take all these exponents and bring them out front in front of their respective ln's. So now I have f of x equal to ln x plus 2 ln of x squared plus 1 minus 1/2 ln of 2x cubed minus 1. And so there is my function expanded out from pre-cal algebra days. Now I'm going to do my calculus and my derivative. So I'm going to say f prime of x is equal to derivative of ln x is you put whatever you're ln in on bottom and its derivative on top. Plus, I'm going to go ahead and draw my fraction bar. That 2 is going to go along for the ride, so I'm going to put it there in the numerator. Whatever I'm natural logging is going to go on bottom, x squared plus 1. And whatever its derivative is, I'm going to place on top, so 2x. Minus, I'm going to go ahead and put that 1/2 onto my large fraction here. Whatever I'm taking the natural log of is going to go on bottom. And its derivative, which would be 6x squared, is going to go on top. And so you can see that has really made my life so much better because I was able to do 3 individual logarithms versus having to do quotient rule, product rule, chain rule, and logarithm. Now, the only thing I want to just kind of check and clean up is right here. I'm going to put that 2 and 2x together to give me a 4x. And then I'm just going to leave these as separate fractions, but I am capable, and you are capable with our algebra, that we could put all of this together. And it looks like we could take one more simplification. I could take this 2, and 6 over 2 is just 3. And so I could do 3x squared all over the grouping 2x cubed minus 1. And so that would be my final answer. But you can see algebra was so helpful, and then we were able to just do our calculus concept of the natural log. Now let's look at natural log and trig. I know you've been missing out on them trig functions this section. Well, the same is going to be true with our trig. Now you're going to notice that I have ln of the absolute value of cosine x. And if you remember within the domain of natural log, it had some restrictions. It had restrictions of the fact of I can't take the natural log of certain values, and those values can't be negative. And that is based on the fact of going back to your algebra pre-cal days. And so with this, when I'm looking at cosine, because cosine is a cyclic function, you know the shape of it from previous courses, and you know that based on your trig circle, how it goes around. So I am going to have the absolute value on the cosine x, and that's to restrict its domain. And then, so when I go to take its derivative, I'm still going to approach it the same way. I'm going to say, okay, well, its derivative is going to be equal to whatever I'm taking the natural log of, which is cosine x, times on top its derivative, which is negative sine x. And then because I'm good with my trig, I know that that reduces to a negative tangent x. So make sure you're staying on top of those trig derivatives and then also the trig equivalencies. Let's look at the next one. F of x is equal to 6x squared times ln of 6x. So we are going to have to do product rule, and we're going to have to do our natural log. And so I'm going to say f prime of x is equal to product rule, derivative of the first, which is 12x, times the second, ln 6x, plus the first, 6x squared, times the derivative of ln 6x. So you put your 6x on bottom and its derivative on top. So this is my raw derivative, and I'm going to clean it up. I don't have quite of a cleanup in that first term, so I'm just going to leave it. Plus these 6's are going to cancel. This x squared is going to cancel on this x, and so I'm just going to give a 6x. And then lastly, I could factor out what they have in common. I can see that they both have an x in common in those two terms, and they both have a 6 as a greatest common factor. So I'm going to factor out the 6x, and that leaves me with 2 ln 6x plus 1. And then you know what? Let's just go ahead and pull in some of our algebra facts. Let's move that exponent back up. So that gives me ln of 6x squared plus 1. And so we now have a fully simplified, kind of finished out product there. So I hope that working through these examples have been beneficial to you to kind of see the ins and outs of what's going on. If you need any additional help, please reach out. Let's continue on and look at what's going on with our e functions, and let's look at some more difficult functions than just the ones we saw earlier in the lecture. So remember, when you have the derivative with respect to x of e to the u, this was earlier in the lecture, that's just rewrite your e times the derivative of the exponent. And so I'm saying, okay, let's take that approach. So my derivative would be y prime, let me stick with my color coordinating I had there, y prime would be equal to, rewrite your e. times the derivative of your exponent. And then just, it's a matter of formatting. We like to put that coefficient in the front. Not too bad. Let's do a little bit harder. Y equals negative 3 over x. Okay, so the derivative is going to be, rewrite your exponential, times the derivative of your exponent. Now, if you remember what this exponent looks like, negative 3 over x as a function, we could rewrite as negative 3x to the negative 1, just bringing this up. So when I go to take the derivative of that, I can bring the exponent down, which gives me a positive 3x to the negative 2, and then send it back into its original form, 3 over x squared. So just kind of a side note of derivatives there. So it means times 3 over x squared. And then just a matter of formatting and cleaning this up. This would be equal to 3 over x squared. And then this e being negative, we could put it in the bottom to make it a positive exponent. And so that would be the cleanup of it. The next one I really like. I like putting number 3 on like those situations where it's timed and maybe count a high amount of points. I like this one because it has product rule and it has your exponential, but it also has a really nice cleanup. And so this derivative would be equal to, we're going to do product rule, derivative of the first times the second plus the first times the derivative of the second, which is rewrite your e, times the derivative of the exponent, which is just 1. So when I clean that up, I get e to the x plus x e to the x. And I notice they both have an e in common. So I'm going to pull that out front. That leaves me with 1 plus x. And so pretty neat little problem there because it has the product rule, it has your exponentials, but it also has some factoring and cleanup. A few more examples. We've done examples of the logs. We've done natural logs. We've done examples of your e. So let's move into, to end this thing with the examples of a to the x and log base a to the x. So remember, it's very similar to what you're doing with e to the x, but now you're going to have to throw in that log ln of base a. So the derivative is going to be equal to kind of 3 parts. Rewrite your exponential times the derivative of your exponent times ln of the base. And then always kind of clean that up and make it look its best. And so I don't really just need a multiplication of 1 on that one. Let's do a little bit harder one. So again, derivative is going to be equal to, I'm looking at now 2 to the 3x. I'm going to say 2 to the 3x times the derivative of the exponent, which is 3, times ln of the base. And really, there's not a whole lot of cleanup with that one. Just make sure you use your parentheses best you can. Okay, let's look at log of cosine x. Now remember, when you don't have a base, it's like a log base 10. So when I go to do derivative, similar to your ln's, you're going to write whatever you're logging on bottom, cosine x. Its derivative on top, negative sine x. Now because I'm not an ln or a base c, I'm going to have to say ln of the base, which is base 10. Again, clean up. This is equal to negative tangent. So this would be negative tangent x over ln 10. One more. Looking at this one, I'm going to see that it's going to benefit me to do some algebra first and apply some of my log properties. So I'm going to say this is equal to, so this would be log base 3 of square root of x minus log base 3 of x plus 5, so separating out that quotient. I'm going to go ahead and rewrite without the radical, so it would be x to the 1/2 minus log base 3 of x plus 5. And then I'm going to move this exponent out front. Again, we're in red. This is all algebra. So now I'm going to take the derivative of this function. So my derivative would be equal to 1/2 log base 3 of x. So you're going to put the x on bottom, you're going to put its derivative on top, and you're going to do ln of the base. We'll clean that up in just a minute. Minus, draw my fraction bar again, I'm going to put whatever I'm logging on bottom, its derivative on top, ln of the base. So what I'm looking at now is 1 over 2x ln 3 minus 1 over x plus 5 ln 3. And that would be my answer. And again, I could do my fraction trick and put that all together, but again, using that algebra and cleaning up your rational function, turning it into a, kind of all your terms written out horizontally is going to be the best way to look at that. All right, so I hope this went well for this section 2.4. Reach out if you have additional questions.